Good afternoon, everyone.
Hello.
Hi. Did you guys take the vaccine already? I just got my first shot yesterday. My arm is so sore. Let me see. Okay, so I didn't. So we're gonna have a recitation. So basically, we can discuss some question together, and so student dropped me a message about like we can work on some question together. I was thinking I could read the questions before, but yesterday was like it's like I didn't read much. So we can work on the question together, or if you guys have any question, we can discuss together. Yeah. Let me see if I can find the textbook. Let's see. Oh, your textbook is for the whole year? Oh, wait, I need it. Let's see. Oh, it's nice. Like, I know a lot of people get Pfizer, but yeah, I think I don't know, Pfizer and Moderna are pretty much similar. Yeah. Right. Okay. So like before we start, so like you can ask any questions, even from the previous chapter or whatever. So like there's one student, he asked some maybe we can go over something from chapter 10. Question 26 and 32. 36, 22. Wait. So like, why don't you guys tell me your progress? You already finished chapter 10, or you're still working on chapter 10? It's a rotation chapter. with constant angular acceleration. Maybe I can share my screen. Oh, and fluid. Oh, fluid is the last lab we can have, like lab 7. The lab is pretty easy because I think you can finish like a very quick. And yeah, so next lab is like about momentum. I guess it's momentum. No. We just had momentum, linear momentum. Anyways, I don't remember. So chapter 10. Let me see what's there. Oh my god. Relating the linear and angular variables. Kinetic energy, addition. Inertia. Torque. It's a second law for rotation. Kinetic energy. Okay, let's work on that. 286. Oh. Okay, yes. So what do you guys want to do today? We work on some questions together, and or you guys have any specific questions you want to ask? Just a reminder, the lab report due today. So we can let me see. I guess we can. Oh, I haven't internet share. So we work on like a pick a question. How about we work on question like with like randomly from I randomly pick one. So how about 28? So in figure, so then we start. Okay, so in figure 31, a wheel A of radius RA is coupled by the belt B to wheel C. Okay, so wheel AC was connected by the belt B. So the radius 1 is 10, 1 is 25 centimeters, and the angular speed of wheel A is increased from rest at constant rate of 1.68 per second, rate per second. And so this is angular speed. Find the time needed for the wheel C, reach the angular speed of 100 per minute, assuming the belt does not slip if the belt does not slip, the linear speed attitude must be equal. So anyone understand what they says? So basically, when we have when we have belt connected to wheels, let me see. I need to see what you said here. Check. Okay. Feel free to stop me anytime. So basically, when we are have a belt connected together, so the two will have the same angular speed, because let's say if if wheel A is driving the whole driving the whole movement. So if this one get one angular, like a how to say, the um, because it's connected, you cannot like see the wheel A has like a bigger speed than wheel C, because it's all connected. It's like the wheel A is driving wheel C, so they have the same speed, but instead of driving, it's not like on the road driving. They connected with the same belt, basically. So they gonna maintain same angular speed. So this in this question, we just need to understand the unit of the. So first of all, like, we have to understand. Um, so we make the so this is 1.6 rad per square second. Oh, it's increasing. The angular speed is increasing from rise means 0 at the constant rate of okay. So this is the acceleration speed. Rad per second. Yeah. So let's say how long it does it take to so angular speed, they have something. So okay, so let's make clear. So so the first thing when you see a question, try to analyze the relationship um between the objects in your question. So now we have two wheels, one is the smaller one is the bigger one. And the only connection is they have the same angular speed, which means this angular speed is equal to this angular speed. And then you try to find the given information to make the question clear. So you have the radius is 10, this is 25, and this one, so will A gonna start from rest, which is 0, to with the acceleration speed 1.6 rad per square second. So now, and you want to, okay, I need to find to understand the rev per minute. What does this mean? So let me see, revolutions per minute. So it means how many circles, like from our lab, we know it's like how many circles per minute. So we want to find how long does it take for wheel C to reach to the angular speed of 100 revolution per minute. So basically, you have to find the final speed of 100. Okay. Let me see the relationship between. I just forget the equations. Let's see, angular. Oh, someone asked questions. So okay, so yeah, that's a good question. So Alex just asked, do we need to convert the revolution to rads per second square? Because so like before we process, we have to understand the meaning. And okay, let's say what is the rad per square.
Judy,
Yes.
I have a question. Is this recitation mandatory?
Yeah. No, it's not mandatory. If you're Yeah.
Okay,
It's not mandatory.
okay, so I'll see you next week. Thank you.
Okay. Yeah. Okay. So it's basically the so one rad is like a one circle, right? Like going through one circle, and so it how to convert? Let's see. Yes. Yes. I'm a little bit. Let me convert to. Convert to rad. For a minute. Okay, let's try to understand. It's 2 pi radians. Okay, so this 2 pi r. Wait. One revolution is one circle. Wait. Yes, it's 2 pi r, right? So basically, we want to what do you want to do? So we wanted the first one, like let's say, so when the speed of the second wheel reach to 100 revolution per minute, and then we can so the equation, there should be an equation, I don't remember. So angular, how to calculate angular speed. Omega, I think there's some, it has to be with like R. Okay, so let's don't look for any equations. We just look at this one. So now we want to say, okay, so we're gonna start from C and we and go back to A. Then we calculate the time. So when we have the angular speed of 100 revolution per minute, this is speed, and so how long does it take? Like for 1 minute, how long does it take? So my understanding, you guys can give me some other, like maybe fast thinking, like a maybe more shortcut. So my thinking is like we can count for 1 minute. 1 minute is like 100 revolutions. It's basically 100 circle, right? 100 circle times to the um, circum, 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 circumference, right? So the basically the length of the circle, and then so this is the s equal to vt. Here we time t. Wait, I'm a little bit confused. Let me draw something first. So why don't someone else like first tell us like what he thinks?
So,
Okay.
my understanding, and I could be wrong on this, is that in order to we want to have the desired speed, the 100 revolutions per minute, in terms of radians per second, because the acceleration is in rads per second squared. So what you're going to do is you're going to divide 100 by 60 so that you're able to get revolutions per second, and then multiply that times 2 pi, because that's going to give you radians per second. At least I think that's what it would do.
Oh wait, so sorry. You said like a revolution convert to rad is one like is rev times 2 pi is rad.
Well, yeah, there are 2 pi radians in an entire circle.
Oh, okay.
So like radians are a division of the circle, and there are 2 pi of them. And so it doesn't really matter about the radius at that point. I don't think. And someone else can definitely feel free to correct me if I'm wrong. But
yeah, I think yes. So like I just don't remember all the equations, and I learned the things in Chinese, so I have to convert. Yeah, so okay, so like one thing we have to be certain is like the rad. So like 2 pi rad is a one circle, right? So yeah, we want to make the unit unified, and then so we can convert 100 rev per minute to rad per second. So it's like 100 over 2 pi, then divided by 60 is a rad per second, right? Is that
no,
what?
it would be multiplied by 2 pi, because you'd want to have 2 pi radians over 1 revolution. So then the revolutions would cancel. So it's 100 divided by 60 times 2 pi. Should get you rads per second.
Wait, why you have to divide 2 pi?
Multiply by 2 pi.
Yeah, sorry. Why you want to multiply?
Because we are converting the revolutions into radians. Because the units that we're desiring is radians per second. We want to know what that would be in radians as opposed to in revolutions, because the acceleration rate of A is in radians per second squared. All right. I would think that you'd want to have it all in the same units.
Yes. So did you just say like 1 revolution equal to 2 pi r rad?
Yeah, 1 revolution is equal to 2 pi radians.
Radian.
So if you have 2 pi radians over 1 revolution, which is then the revolutions, and you multiply that by 100 revolutions, then you're canceling out the revolutions, and so you get 2 pi times 100 radians.
So the radians is the rad, right?
Yes. So rad is radians.
Okay, 2 pi times radians equal to revolution, and now we have 100 revolution, and then you want to convert to 2 pi. You convert to radians, so
Yeah.
you're supposed to divide 2 pi.
Multiply by 2 pi.
Multiply 2 pi.
100 times 2 pi, because we want to cancel out the revolutions, and so all we have is radians. And so it would be 2 pi radians over 1 revolution.
Oh, yes.
And then the revolution cancels, and so we get 2 pi times 100, and then you divide that all by 60, and then that gives you how many radians per second.
You're right. So it's like 2 pi times 100 over 60. This is a radian per second. And so we know like a v equal to v0 plus at. So basically we want to know how long does it take from 0. So like the wheel C has an angular speed which will be the same as the wheel A. So wheel A will have like when wheel C has 100 revolution per minute, then wheel A have 100 revolution per minute. Wait.
So does that mean that all you would need to do at that point, once you have the relationship, is then get the velocity equation and be able to use that similar to linear velocity equation? So just like integrate the 1.6 rad per second squared so that you get 1.6 times the amount of time, and that'll give you the velocity at any given point in time, and then you set that equal to this 100 times 2 pi over 60.
Yes. So like all the equation we learn from linear is like we can use them like under some circumstance, or like with some conditions we can use in the angular. Let's say so this for this one, okay, thanks Fadia, thanks for correcting me. It's supposed to times for 60. Like the equation when we try to convert. Okay, so I just tell you the when how do you think when you try to solve the question, and you guys can convert all these units. So okay, let me finish this one first. So like so in this case, because they are connected by about, so like if the A move faster, then the B will move faster. Like it's like all connected, and how long, like okay, so here we try to calculate the angular speed. Is we use the circles, we use the circumference, conference, I don't remember what it's called, to divide it by the radius. And for the first one, because it's smaller, the radius is smaller, then it move faster. Wait, let me see. Let me think. I think something. So basically, they are working the same distance. Even for the A has a smaller. Can someone tell me what's the equation to calculate angular speed? It's 2 pi r over t, right? If I'm correct me if I'm wrong. I just like it's been a long time. I didn't look at those things, but like omega equal to 2 pi r over t. So then and then let's just write down omega 1 equal to 2 pi r1 over t, and omega 2 equal to 2 pi r2 over t. Correct me if I'm wrong, okay? I just speaking from my instinct, how to say, but like based my if I don't remember everything, so it's supposed to be that. And so you have the same angular speed. Wait, do you have the similar angular speed? So they work same. You don't have a, do you? You, so will A and will C does. So the only thing we know is they connected by the belt, which means they walk the same distance. So like let's say, I'm a little bit confused. So what do you guys think now? I really am a little bit lost. It's supposed to be, they have the same angular speed, the same, over the same amount of time, they walk through the same distance, right? Yes, radius is given. So basically, so I just try to like understand what is the same, what equals to the two. so we cannot say their angular speed is same, can we? We can only see they work the same speed, but because the radius, so remember angular speed omega equal 2 pi r over t. So when we see the speed, we mean angular speed, because the only thing we are sure is 2 pi r1. Somehow, like they, excuse me, 2 pi r1, 2 pi r1 is supposed to be, they work to the same. I'm so lost. Okay, so the linear speed at the 2 rim must be equal. Linear speed at 2 rim must be equal. What the rim means. Yeah, 2 pi r over v equal to t period of every revolution. Linear velocity. Wait, where's the linear velocity here? We are talking about the angular speed velocity. Yeah, but like what is the linear velocity here? Two pi. Oh yes, sorry, I messed up the equation. Yes, sorry. The v. Okay. So the linear velocity is v equal to pi r over t. It's not omega. Omega equal to 2 pi over t. Sorry, I messed up the questions. Yes, so then we can try to solve the, so the v is equal. So we can say, yeah, it just, so now what do we do? What I do is v1 equal to v1, not omega 1. V1 equal to 2 pi r over r1 over t. V2 equal to 2 pi r2 over t. And so like let's try to convert. Can we r, oh wait, so v equal to omega r, right? R times omega. And then we try to convert the angular speed to the linear velocity. Okay, then now we find the connection. So we try to see, okay, so basically we'll see has a linear velocity is like 100 revolution per minute times R2, which is RC. Okay, RC. Then we find R, because the two has the same linear velocity. Then we can try to find so v still I'm okay, so we find the linear velocity, and then we can convert. Okay, so v equal to like let's say 100 revolution per minute times r, which is 25. No, we have to make it like a unified 0.25 meter. Like we all use like the international unit, right? And then we can use this velocity applied to wheel A, and then we try to calculate its angular speed, which you use omega r c over r a. This is angular, this is omega A. Do you know what I just said? I just write it down. Omega A. We try to calculate omega A, right? Omega 1, let's call it omega 1. Omega 1 equal to omega 2. So omega 1 means will A, omega 2 means will C. Omega 2 times R2 over R1 over R1. And then after, and omega 1 equal to omega 0 plus AT, right? We can use this, and then omega 0 equal to 0, A equal to 1.6 rad per second. So you try to solve T. So so like any question for this? Just took me very long to figure out the linear velocity and the angular speed, angular velocity, and also like we convert the revolution to radian. So what do you guys think now? Okay. Sorry about the earlier. It's supposed to be very easy, and I just don't remember the equations. It's been a long time. But yeah, I should have prepared yesterday. Well, anyways. So do you want to work on another one? I feel very sorry. Okay, so we can say, this is recitation. It's not mandatory. So like, if guys feel like why it took me so long to remember the equations you just learned in the class, you can, like, if you find this, just feel free to leave or to stay. Okay, show early method of measuring. Okay, how about we look at 29 or 29? Okay, we can just random start. It work together. Also, I'm learning from you guys. Evens, okay. So does it have any 32? Okay, let's work on 32. So like an even or odd, they have a certain like meanings. Like maybe even is more, I don't know. Oh, okay, I see. Oh, okay, I see. Okay, let's work on the even, the 32, question 32. A car starts from rest and moves around a circular track, okay, of a radius 30 meters. Its speed increases at constant rate, okay. I like the use meters. but it's like it doesn't matter whether it's used meters or rad. You just have to know the the core, like the understanding. So it's all same. It's circular. Like even a car is riding from a circular track. It's still like a circular motions, right? What is the magnitude of net linear acceleration? What is the magnitude of its net linear acceleration 15 seconds later? Linear acceleration. And what is the angle does the net acceleration vector make with the car's velocity at this time? So 30 minutes, okay, it's increased at the constant rate, at the constant rate. Okay, so from rest means from zero. From zero, it's also like a speeding. So basically, so like you can take okay, the first question. So the first question, try to understand. So my understanding, you can bring your own understandings. So we try to figure out after 15 seconds, what's the speed? What's the linear solutions? Okay, what's the speed of the car, right? So basically it's from zero, and now you can just look at the car. So like v equal to v0 plus at. So the a is here, and the 15 second is time. So v equal to at because v0 equal to 0, and v equal to at, which is 15 times 0.5, 7.5 meters per second is a magnitude of its linear acceleration. So what do you guys think? Yeah, because it gives you 0.5 meters per second. It's linear. Okay, so but sometimes it's tricky. It depends on their unit. You just can't tell. Yeah. So okay, if no question, then we. Final velocity. Yes. So this question we have to find the velocity. So linear. I think it's asking the linear velocity. What's the magnitude of this net linear acceleration? And then, okay, question B, what angle does this net acceleration vector make with the car's velocity at this time? So basically, they want to ask you to find the, like how many angles, like we see if there's a circle, it starts accelerating. So basically, how you try to find the angle. So basically, you use the distance, which is a circular circumference. Right? I'm very sorry. I feel like I'm not very circumference. So we know how long it works. Not works. The car has driven like from the rest to when it reached to the speed 7.5 meter per second. And then then you can try to see how what the angles are. So remember the angle, you can try to see omega equal to pi over, wait. And so the equation for, what's the equation for that? Then you have like a final, so in the end, you have the final velocity, linear velocity, you can convert to the angular velocity. I just don't remember the equation. Linear acceleration. Okay, so but like what you get from by calculating v equal to at 15, 0.5 times 15, it's your linear velocity is not angular anything. So like when we see all the linears, I think that when you use the meters or something. So
No, what I was saying was then it's saying in the question what is the magnitude of its net linear acceleration, and as the acceleration that's happening is at a constant rate of 0.5 meters per second squared, I don't think it's just 0.5 meters per second squared, but it's not asking for what the linear velocity is 15 seconds later. It's asking what the net linear acceleration is, which I don't remember specifically, but there is some element of there's acceleration in going in an angular when turning, which is why you could be going the same velocity, but you're still accelerating because of the fact that you're turning as you're doing it.
oh yeah, I see. So yeah, for the speed has like constant rate, like a acceleration speed, but because it's working on the circular track. So what's the linear acceleration means here? So so can you say that again? What do you understand the linear acceleration?
Oh, I don't know what what the linear acceleration should be actually getting to. I just meant that like if we say that the linear acceleration that the car is speeding up with is 0.5 meters per second starting off, then if it's a constant rate, then you would think that it would be 0.5 meters per second squared 15 seconds or 20 seconds later, because it's increasing at a constant rate. But I don't think that that's what it's asking for. It's asking for the net, and the net is the part where I don't remember how acceleration works in a circle separate from when it works just in a straight line.
Okay.
So I think if you look at 10 TAC 3, section 10.3, there's the acceleration seems to have, it says at the key ideas right there on the first part. If you want to go to it, it'll be easy to view it. You should go to section 10.3 in the textbook at the very beginning.
3.
I think it's page 296.
Thank you.
Mhm. Yeah, right there. I think you just went past it. Oh wait, sorry, 296 in the PDF. It's 268 on the actual page number. Sorry about that.
Okay.
So you see right there under key ideas on that page,
Key idea, yeah.
and then you see the linear acceleration has both tangential and radial components. And so I think the tangential acceleration is what's given to us, the 0.5. And then you also have to find the radial component, which is v squared over r. And then I think the magnitude would be, at squared plus ar squared, square root of that. Do you see what I'm saying? Since it says that the linear acceleration, which is what it's asking for, has two components,
yes.
I think that we would need to find both of those.
Oh, I see. Tangential and the radial component. Oh,
Yeah.
that's
And I think the tangential is what's given, yeah, if I'm not mistaken.
Yes. I think, yeah, your understanding is correct. So like they are asking the net linear acceleration. Oh, I see. Oh, wait a minute.
So I think we need to find the linear velocity, which we could just by, that's the the a times t, which would be 7.5. And then we plug that in for v squared over r. And then that would give us AR. And then the magnitude would be AT squared plus AR squared, square root of it.
Wait, why is v squared over r not v over r? Wait,
It just says right there on the, let's see the next one.
Oh, yeah.
Yeah, the radial component of it, I guess.
Yes.
Has the tangential and the radial component, yeah.
Mm.
So I think we could use the tangential component because that's like the linear accel, I would guess, in a way, because it's, the tangent that's going. And I think we could find the v, the linear velocity, using that, like you said, would be 7.5. And then we do 7.5 squared over r.
Yeah. Yes, I got you. So then we can tell them like the tangential and the radial component separately. We don't need to combine, right?
We don't need to come back? No. Yeah, I just wanted to show that. I think that's the key to this problem.
Mm.
But the question is, though, is the net acceleration going to be just that tangential? And if it is, are we taking the angular acceleration tangential component of it, like the angle that's being made?
Well, it says the reason I think that is because it says the magnitude of net linear acceleration. So I would assume the linear acceleration has two components. And then since it's saying magnitude, typically I would imagine with most magnitude, you'd square both of the components and take the square root. Does that, if we do that, can we just check? Is this answer in the answer key or no?
It's not.
Have we tried Googling it? Let me try Googling.
So why they give you a tangential component AT equal to AR?
Because that the A in that other is alpha, and it's alpha, which is the angular acceleration times the radius.
Oh, this is alpha.
We don't need to know what the angular acceleration is because we're given the linear acceleration AT. So we already know what that is.
Oh, yeah.
And then the AT plus AR would be the two different components of it.
I did just Google it, and it's Slater, so I don't know, I'm sure it's probably accurate. But it does, yeah, it's exactly, yeah, we do use the t equals 15, and we use the 0.5 times 15, 7.5, and then we plug that into the AR, and then we do exactly the A net, the magnitude is square root of AT squared plus AR squared.
That's the one part that I'm still not getting. I agree that you're right. I just am not understanding why, because if those two components, like, I guess they're going in opposite, they're going in two different directions. Is that the whole point? And we're getting the acceleration net is the hypotenuse of that triangle that's being created. Is that the way that I'm supposed to understand?
I guess it's, yeah, I don't fully understand it either, if I'm going to be completely honest. The only reason that I thought that might be it is because I saw the word components, and then when I think of components and magnitude, it's typically how it goes. But no, right, yeah. I don't fully understand it either, honestly.
Okay.
I guess the tangential and the radial components, like I'm not very sure. I guess tangential. maybe we can leave this too, because I think, so for some reason, I think it's like a XY, like you always, I'm not very sure. Yeah. Maybe I can ask my other TAs to see what their idea. So you guys prefer, like, we present the tangential and the radial components separately?
Yes, you get the two components separately and then square and get the square root of them.
We can take that for now. Yeah. Okay, so the second question they're asking, what? Let me see, go back. It's 20. Okay, here. What angle goes? So we can, for now, we can say the magnitude.
For the angle, we would just then take the, I guess we would need to find out, make sure that we get the appropriate angle, take the one over the other and do the inverse tan. The one component over the other component and the inverse tan of that relationship, and that's going to give us our angle of rotation.
Angle is like it's red, how many radian, right? Like you go through like say from a circle, like how many angle the car has.
Radians or degrees.
Yeah.
My guess is that this would be asking for degrees, which is, I mean, not that it matters. It's as long as.
Yeah, you can always convert. So like another way we can do it is like we calculate the distance the car has walked, and then if we call that S over 2 pi r, which is a circumference, equal to the angle x over 360. So we get the angle. So basically, the distance the car worked on a circle represents the angles in 360 degree, right? What I want to see is like a share. So the distance over, so like this is a car. No, this is a circular track. The car start from here and keep walking. I mean, keep driving into here. But you see, this angle we try to find, and this distance, this distance to the whole circle is equal to this angle to 360 degree.
But it's not asking what the angle of this, well, how much of the angle of the circle that was, of the track that was gotten to. It was asking what the angle was between that net linear, that net acceleration that we figured out, because that's got a direction angle to it with two components. and figuring out what that is in relationship to its velocity, which I'm guessing is the direction that it's going on the track. So we would want to have, I would need to draw it to give a better example, but there's a picture that I think is helpful on page 270. That's a similar sort of thing.
Wait, what angle does this net acceleration vector make with the car's velocity at this time?
Right.
So you mean it's not asking for this angle?
No, it's not.
Okay, what they are asking?
Go to page 270 in the book. 270.
270. Okay. Here. So
I thought you were going to bring it up on the screen.
oh, you cannot see. Oh, sorry. This one?
Yeah, that image. So what we calculated, I think, is that hypotenuse line, that net acceleration. And so what it's wanting to know is not the theta that it's showing in the picture, but the other theta that is with the tangential acceleration, because that's the direction of the velocity, I think.
So if, okay, let's say if this is a car, this is the circular track, then what do you think the direction? So which was the tangential?
So
Straight.
if you look at where the point is, where the next to the theta, so
Mm.
we're saying that the car is at that point, and that hypotenuse line, that diagonal line there, is the net acceleration that we figured out, and then the vertical line, I think, is that tangential acceleration, I think, is actually also the same direction as the velocity. So we would want to be figuring out the angle between the tangential and the net accelerations. So
I think Alex is perfectly right. If you actually go to the page right before it, 269, there's a picture there that makes it look very clear. Those two pictures right there. Scroll up a little more. It'll show you because he's 100% right that the V is parallel to the tangential and then the radial. And I think he's right that the net accel was exactly what he said. It was the hypotenuse there between AT and AR.
And that picture also helps me better understand what you were saying, Windsor, which about the it being the AT is that tangential is going in one direction and the AR is going towards the center, and then we want to actually, in order to find out what the net is, we're actually combining those, and that's giving us our.
Oh,
yeah, that picture helped.
Yeah, also so that from here, yeah, I think, yeah, we maybe should combine. So can someone repeat the questions for what the second question asking? I mean, from the
it said, what angle does the net acceleration vector, so I assume that's, like you said, the hypotenuse there, make with the car's velocity?
Oh, I see. Yes, with car's velocity. This is the car's velocity direction, right?
Yes.
And they are asking the net, which is like we come back like here, maybe somewhere.
The net would be somewhere like there, and the angle between the net and the velocity.
Yes. Oh my God, you guys know everything. Okay.
Well, Windsor has been reading, which I think is cheating.
No, that's why we need this what's it called, this recitation, because I would not have figured this out on my own. I would have been like, oh, I don't know.
Yeah, I'm kind of like that too, which is that, like, I can ultimately figure these out, but I have to watch 7 videos, spend 4 hours on it, and then it's like, oh yeah, I'm supposed to do 80 more questions like this. It just
Exactly.
Yeah, I think a recitation is like a good chance for you guys to discuss. Like a it's not like always like other people tell you what to do and you figure out you see you guys like working like even we're like doing some discussion, you think like very creatively and try to figure out the answers, and then you bring me the answer. I think that's like, incredible. You show me the answer. I think that's is like, yeah. Anyways, wow, that's interesting. Also learned. So you guys want to do one more, or what do you guys think?
I'm down
Sure.
for one more.
Okay. Let's go back. So we'll do one more even question.
Yeah, and we can go into the next section since
Next section.
or even do one of the additional problems or whatever if somebody has a preferred section that they want to go over. I just 10 seemed like it made the most sense to be hitting pretty hard now since we had just finished with 9 in the last exam.
Oh, so like they have questions for different like sections, like in kinetic energy. Oh, that's clear. So anyone who want to do like another question, we can do it together.
Maybe correct me if I'm wrong, but didn't the professor say that we won't ever have to calculate rotational inertia? Like that will always be given to us?
I'm not sure. Like other students can answer.
Actually, I don't recall. He very well might have said that, but I don't remember.
Because I that was one thing that I was like, I made sure to. He had said it multiple times. It was like, you will never. I will always give you the big I, which I think is the rotational inertia.
I think you're right. That sounds familiar.
Okay, so then if that's the case, then I guess we don't need to worry so much about 10.5 if that's calculating the rotational inertia, since we'll generally be given it. So maybe we go to like 10.6. Or 10.6 has all one dot questions for torque, which is unfortunate considering like
easy.
Torque is well, torque. Those are easy questions probably because they're one dot, but like torque is difficult for me. I would say maybe we do then like 50. 51's an odd. 52.
52. Okay. This is Newton's second law for rotation. So you see, we can like use Newton's Newton's second law in the linear and the rotational. So let's say, in this figure, I like the question with figure. I feel like it's easier to understand. Okay. Cylinder having a mass 2 kilogram can rotate about the central axis through the point O. This is central. Forces are applied as shown. F1. Oh, they have multiple forces. F1, F2, F3, F4. So you can like when you are really working on the question, you just write down the forces like F2 equal to 4 Newton, and you write all the information on the graph. Also R equal to 5 centimeters, and wait, R small r. This is small r, and a big R is here. I try to figure out a cylinder. Okay. Why is small r? Oh, because why they give you a small r and a big R? I guess because the force is applied in a different position. You see, 1, 4, 2, they applied on the big R, which is like you apply the R to the on the very on the surface. I'm not on the surface. It's so it's not so it's with the big R. The small r is like when you apply for F3, it's 2 Newton, but it's inside the R. So like it could have a effect. Let's say if you were applying the same amount of force to different position of a rotating object, it will have very different reactions. So we just keep that in mind that 1, 2, 4 are applied on the big R and the F3 applied on the small r. So find magnitude and magnitude or direction of the angular acceleration of the cylinder. So basically we try to wait. Maybe not. Maybe it doesn't have any effect. Let me see. So let's try to make a x. Let's say this is x, this is y. Maybe we try to diagnose the force.
But wouldn't again, I'm really not sure about this at all. But wouldn't F1 and F2 be just in opposite directions because they're both tangential with the cylinder itself? So that pushing that's being done should be in just like opposite directions, even though it doesn't like actually look like it's opposite directions based on the picture.
So you think they are opposite directions because they are tangential?
Yeah, they're tangential and they're tangential going in opposite directions. So like F1 is tangential going to the left and F2 is tangential going to the right.
Let me see the questions under the solution. But you don't know the angles.
Does the angle matter given the fact that the force is being applied tangentially? I'm not saying I'm right. I'm just,
I know. I just try to think. So you mean F1 and F2, they can cancel out? But
well, I mean, they wouldn't entirely cancel each other out because F1 is 6 and F2 is 4. But my guess is that the net would be 2 in the direction of F1 if I were understanding it correctly.
But why I feel like if let's say if F2 is on this direction, like clearly on the bottom, it can be canceled and maybe cancel something. But since here we don't know that, I don't know how we apply. How can we break the forces to the x or y directions? So tell me what's the difference between, I mean, only for the direction or yeah, what's the difference between F1 and F4?
The difference between F1 and F4 is actually pushing from the center of the cylinder outward as opposed to pushing tangentially from the cylinder. So if anything, it would be moving in a completely unaffecting direction from F1. So it wouldn't change anything about the magnitude of the spinning because it's not actually being pushed in a direction that will rotate the cylinder left or right.
Yes. Let's say, but it's always pointing to maybe the same direction. I mean, I'm not sure if this is like a straight angle or not.
Given the fact that everything else has the right angle signs to it, that it would the fact that it is trying to connect that as one straight line is, I think, would mean that it is in fact a straight line.
So it doesn't. So does it means it doesn't matter if you're applying here or here, as long as you apply a force in the same direction, you can combine, you can merge them.
I'm saying that those aren't combining because the fact is that one is being applied tangentially, so it's causing the cylinder to rotate, which is F1, and one is being applied from the center outward, which is not tangential to the spinning or tangential to the cylinder. So there will be no net effect of that force on the spinning of the cylinder.
I see. Yes, because we cannot like minimize this cylinder as a point or something, because it's rotating. It has its own motions, so we cannot like just say, oh, this is a point, and then we see all the forces. We cannot say like the force is to minimize to one because this force F1 and F2, they're having effect on the their tangential speed, right? Tangential
Yes.
speed.
I mean,
Oh yes, I know what you mean. Yes.
They're having an effect on the spinning of the.
Yeah. So how about
I scrolled back up in the textbook to this section, and I think because this is asking for the angular accel, and it gives the formula net torque equals inertia times angular accel. So I think if we found the net torque, would probably be the first step. And I think F4 probably wouldn't be relevant because torque is the what's it called, the component of the force that's perpendicular. And F4 would have no component that's perpendicular.
perpendicular? Yeah.
So my next dumb question is, obviously, like, we don't know what the rotational inertia is because it's not given to us. So what is the other way of calculating torque? Because I mean, what, like, is,
Well, I mean, I know the professor said the inertia will be given to us for him, but I think what's inertia? It's mr squared, right? And we get or 1/2 mr squared. I always forget which one it is, but and we have the m and the r, so we could, you know what I mean. I'm feeling for the textbook problem, it might want us to calculate it.
Want us to calculate.
Yeah,
so,
exactly.
Yeah, because if then we had that, then we would be able to have the net torque.
Exactly. Yeah.
But torque is the force times what's
Radius.
force times radius. So, so
the net torque might just be the sum of all the torques from the different forces. Yeah, exactly.
Right, exactly. Yeah, that's kind of what I'm thinking. So also, yeah. So then what we would do is we would figure out what I is. So we get the net torque, we divide by I, and that gives us our angular acceleration. Yeah. That makes sense.
Yeah, I think that's exactly how we do it.
And so then that way, with each one of these forces, so for F1, that force times, but is, wait, so torque is force times radius?
Yeah, I guess so. I just go.
It's like the component of the force perpendicular to the radius, I think.
Component of the force.
Yeah, it's F perpendicular to R times R.
Okay, so we would just do that.
Yeah, so that's why I think F4 wouldn't be relevant, but the other ones
Right.
would be.
Oh yeah.
Yeah, and so then it would be F1 times our big R plus or minus F2 times our big R. And then the other one is it's going to have some, and it's going to be moving in the direction of the minus some component of F3 that's tangential, which we would need to figure out. So
I mean,
F3.
if you calculate torque, then you just multiply by the small r, F3 multiplied by.
But it's not but it's not. That's not tangential though, because what Windsor said was that it was the tangential force that's being applied.
Yes, tangential means like a perpendicular to the radius, right?
Yeah.
So
F3 is perpendicular to the radius.
Yeah,
No?
it's perpendicular to little r, I would assume.
Okay.
Yeah.
Sure. Okay, I see now. That image is not super helpful.
I know, it's a terrible image. It's scary to even look at.
Yeah, okay, I see now. So it would actually be doing the same thing. The only reason why it did smaller was because it wanted to make sure that we were seeing it in that respect. So then, okay, so it's F3 times little r, but it still is F1 times r minus F2 times r minus F3 times r gives us our net torque.
Mm. What's the physical meaning of torque?
I mean, yeah, it's the force that can cause an object to rotate about an axis. So that's all the forces that we've calculated there. And then the inertia is the angular inertia is, hold on a second.
Why we want to calculate inertia?
Because we divide the torque by the inertia to give us the angular velocity.
Oh.
And so the inertia is, yeah, the rotational inertia is the sum of all of the m's times r squared, which do we know what the mass of this is? Oh, yeah, it's 2 kilograms.
2 kilograms.
So it's just because it's one object, it is just the one thing. So it's the 2 times the radius squared. So 2 times big R. And so the torque we finally get is the net torque divided by the inertia, and that gives us our angular velocity, our angular acceleration.
So torque divided by the inertia is the acceleration.
Yeah, exactly.
Interesting. Square.
But again, we only have one mass and one radius, so then it just becomes the
inertia. So we only calculate the big R.
Yeah, we only calculate the cylinder is the only mass, and the radius is the radius. So then we take that mass times the radius squared, and that gives us our rotational inertia. And so the torque divided by the rotational inertia that's calculated gives us that angular acceleration, or at least the magnitude of it.
Yeah, how you define the directions? Direction.
I don't know.
Direction.
I mean, isn't it just asking for whether it's spinning to the left or to the right, or is it actually looking for something more specific? Because given that the way at least I set it up, spinning it to the left is positive and spinning it to the right is negative, then whether the number is, whether that angular velocity is positive or negative would tell us that aspect of the direction.
Yeah, that we don't. I think so, because we don't have any like angles specified. So I guess spinning right or left is either way could be the answer, because we don't really know directions. Directions is left and or right, right? How we guess?
Well, that's the thing, is I don't know what they mean by direction. Like if it's just left or right, then that we just make the determination on positive or negative. But if it's looking for some kind of like calculation of the angular acceleration in some like aspect of net thing where we'd be doing some kind of finding a hypotenuse thing, that's the part where I just don't know.
I agree. Try to think if we can do anything with the direction.
I think it might just be asking for clockwise or counterclockwise, which I can't remember if clockwise is negative or positive, but since
it's whatever we make it.
Clockwise is like clockwise is like this, but we can define like
yeah, we define the direction in terms of clockwise versus counterclockwise at the beginning. I defined counterclockwise as being positive and clockwise as being negative for no reason other than just that was what I did.
Yeah, and since we get the angular accel, I think I'm pretty sure it ends up being positive if I did my math right. So then it would be, I would assume that's probably the answer. Then it'd be counterclockwise if counterclockwise is positive. I just can't remember which way is positive, which way is negative.
Yeah, I think he did clockwise as being positive, but he made it very clear that it's like it doesn't matter what you choose as long as you just stick with it for the whole problem.
Oh yeah, as long as you're consistent with it.
Right. Glad you actually punched in the numbers, because I wrote out all of the equations and then I was like, that's good enough, right?
Yeah, like I said, I think hopefully I did it right. But yeah, I mean, either way, as long as we conceptually get it,
Yeah, I mean, understanding how to build the equation, because that's the biggest thing. I mean, I have to say that like on the last exam that we had on Wednesday, like one of the biggest problems I had for the ones that I missed were just that like I didn't set it up correctly because I was just not conceptually making the right connections as to what I needed to set up. But for everything I set up correctly, it's just plugging it in, and that's easy enough. And I was able to get the right
yeah, absolutely. No, yeah, it's the arithmetic is never that difficult in this class. It's always just setting it up. That's always takes me forever.
And the worst part was like the spring one I messed up, which I feel so dumb about, because like my initial concern was like I got to make sure to remember that it's when the work equals each other, not when the forces equal each other. And I got to the exam and I was like, when the forces equal each other, and I'm like, dang it. I did it wrong. But yeah, so keeping that stuff straight and being able to understand how to build that torque equation and recognizing what that means is going to be the big thing here, I think.
Yeah, I agree.
I'll also get in some more practice. But I think that works for me.
So like I still have one question here. So when we try to define the direction or like a left or right, so like you add up the forces, you
We're doing it based. So when you figure out the answer for question A, the magnitude of acceleration, you know, it's just saying, yeah, it would be if it's positive clock or counterclockwise. If it's negative, then clockwise.
Okay, that's good question.
Thanks for the help, Windsor. That's been really informative.
No, thank you, man. No, likewise. Yeah, that's it. So, I mean, I appreciate you doing this, doing the recitation this week. I would like it if we continue to do these through the final, because this is being able to bounce this off other people, and it makes it so much less stressful than just trying to figure them out by yourself.
I'm 100% with you, and I would like that. And like BT Dubs, Windsor, and for anyone else who's listening in and wants to partake, I would definitely be down for getting together more often to just do stuff together, because I feel like we would be more quick in a group effort than individually. But you know, whatever.
Yeah,
Especially once we get close to that final, because this class, it really seems like, at least for me personally, I can say that this is all going to come down to the final. I mean, especially the way he's setting up the grades, I'm like, this is all going to be on the final.
Yes.
So
it's really all going to come down. I 100% agree. And I mean, to some extent, that makes me feel a little bit better because of some of these exams that have happened. But on the other hand, it's also like, okay, everything comes down to just don't mess up. Don't mess up.
Exactly.
Don't mess up.
Cool.
We can definitely have the recitations. I think also like there's a good learning opportunity for everybody. So I was thinking, let me think. The next week is lab, and then the coming week we can have the recitation and then lab and the recitation, or maybe you have finals already. Yeah. What I remember, I want to ask another question. I forgot what I'm gonna say. Oh yeah, so I remember at the beginning of the semester, you guys have a have a student group. Do you discuss a lot in the student group? I mean, I don't Discord, right? I mean, we can definitely move here. I'm just curious how often like you discuss questions there.
From what I see, it's mostly talking about the labs. It's mostly trying to figure out, you know.
Also, like what time due, the homework due, or whatever.
Yeah, that's typically most of what I see in there.
Okay, I see. I saw like you guys are gonna. So you guys are on the same class, physics class. I mean, not lab, the class from the same professor.
Yeah,
I'm pretty sure we're all on the same one. Yeah.
Yeah.
Okay. And at the same time.
Yes, we all have the same lecture time. I in fact, I think, I mean, like that's there are a bunch of kids in the class, like some 180 or something. So I think it's like at least half of, or if not more, of all of the students taking physics this semester.
Also, if it's in person, you all classmates, like pretty much go to the same classes. Wow, that's nice. So yeah, I guess. So what do you guys want to do next? I mean,
I was figuring we would be wrapping up because I gotta do prep for my next class. But
all right. Yeah, that was good. Then we can have the regular recitations. I can prepare before, and I hope you guys can take the vaccine soon.
Great. And what I would say is maybe if you want to do some prep, I try to make sure to send notices earlier, but like I don't exactly know how much progress I make on work and stuff, and so sometimes I might make more and sometimes I might make less. But I would assume that we're not going to have our exam before 2 weeks from today. And so, if that is in fact the case, then something that would be either something in late chapter 11 or in chapter 12 is, I imagine, where we would be at that point. And so, doing problems from probably chapter 12 would make the most sense.
Okay, so let me see. You mean the exam for final or like just a midterm?
It's one of the midterms. It's the last quarter midterm. And
Okay.
that's going to be 10, 11, and 12. And so I figured by that point, we probably would. My guess is that we'll need to be something close to being ready to be done at that point. So,
Okay, then we can like meet on May 4th. I guess we can do maybe before your exam.
yeah.
Yeah. Okay. We'll try to like see some questions from chapter 11 or earlier.
From
topic.
chapter 12 is what I'm thinking, probably.
12.
Yeah. So then that way you can at least know like same sorts of situation as what we did today, just finding some of the 2 dots and harder questions that are evens from that particular area.
Okay. Thank you. I really apologize for today. I didn't, but yeah. But I think it's good. Like everybody contribute to make the discussion more interesting. But definitely, I'll prepare something next week. Next time.
I didn't give you much prep, so I appreciate it all the same.
Thank you.
Oh yeah, thank you. We appreciate you being so flexible with it. Thank you.
Thank you, guys. Have a good day.
You too.
Take care,
Bye.
everyone.
Bye.